Hi everyone, welcome back to our organic chemistry series. In the last lesson, we learned about alkanes, their formulas, and how to predict boiling points. Today we're going to expand on that foundation by exploring saturation, cycloalkanes, and the concept of degrees of unsaturation, which will help you analyze molecules more efficiently in US National Chemistry Olympiad problems. Let's start off with saturation. A molecule is saturated if it contains the maximum number of hydrogens possible for its carbon skeleton. Alkanes with the formula CN(H2N+2) are saturated because every carbon has 4 bonds and all extra bonds are with hydrogen, as we saw in our last lesson. Every single carbon is single bonded to another carbon, and the rest of the free or / extra bonds it has are with hydrogen. But what happens if we form a ring or a double bond, for example? So we're going to move on to the introduction of cycloalkanes. These are alkanes where the carbon chain forms a ring instead of being linear. So now we have closed ring systems made of carbon. Here we have cyclopropane, cyclobutane, and cyclopentane. As you can see, cyclopropane, prop stands for 3 carbons, so as a result, this is a 3-membered ring. Cyclobutane, but is stands for 4 carbons, and as a result, it's a 4-carbon membered ring. Pent stands for 5 carbons, and as a result, it's a 5-carbon membered ring. So this is just so that you guys can tell the importance of knowing your prefixes, as this is mostly what you're going to be tested on the exam as well. And cyclo is just a prefix for when it's a closed membered ring system. So these are alkanes where the carbon chain forms a ring, as you can see. And let's analyze the formula of the cycloalkanes a little bit so that we can jump back to saturation. So we have cyclopropane, which is C3H6, cyclobutane, which is C4H8, and cyclopentane, which is C5H10. As you can see, the formula for these is CN(H2 ₙ). It's not CN(H2N+2). So this one is for cyclo. This one was seen for the saturated linear alkanes. So what's happening here? Don't memorize these yet. It's just I really want you guys to understand what's happening here. Why is there a discrepancy between the formulas if they're both still alkanes, which they are? Like this, despite this difference, they're still both alkanes. Why is this? Well, let's look at this example between propane and cyclopropane. As you can see, propane here is C3H8, and it's linear, meaning it's not a ring. I highlighted the 2 hydrogens which are missing from the cyclopropane, which is the 3-membered ring. And I really want you to understand here that when that ring forms, notice how in propane there are two external carbons, which means the external carbons are only bonded to one inner carbon, which is this one. Remember, inner carbons are bonded to 2 carbons, whereas the external carbons are only bonded to one singular carbon. Linear carbons or non-membered ring hydrocarbons don't have... I lost my train of thought completely. I'm so sorry. But what was I saying? Non-membered ring hydrocarbons, essentially, they have external carbons, whereas membered rings don't have any external carbons. They're technically all internal because each and every single carbon is bonded to 2 other carbons. As a result, there's no space for that extra hydrogen, which is seen in the external carbons in our linear hydrocarbons. As you can see, there's an extra hydrogen they're bonded to. And so, as a result, those 2 hydrogens are lost, and instead we see this bond forming between 2 carbons. So that's why those two hydrogens disappear when we are in a cyclo version of the same compound. So that is called unsaturation, because that means the compound does not have all possible hydrogens that it could be bonded to, because of either a double bond or it's in a ring, as you can see. So double bonds, triple bonds, and rings cause some form of unsaturation, which means it just doesn't have all the possible hydrogens it could be bonded to. I know I mentioned double bonds and triple bonds, but we have not studied compounds containing these or what they're called. So I will give a brief intro into compounds containing double bonds. These are called alkenes, not alkanes. And it just means there's at least one double bond present. So as you can see, let's look at propene. Like I said, the prefix prop means 3 carbons, but the ending is now -ene, so that means there's a double bond present, whereas in propane, prop is still the same 3 carbons, but ane changes because that means it's only single bonds between those carbons. Now, as you can see, the formula for propene is C₃H6, which matches CNH2N. This will ultimately end up being the formula for alkenes, but you don't need to know that yet. Just fun fact. And for propane, the formula ends up being CnH2n plus 2. And remember, N is the number of carbons, which is the formula we know for saturated alkanes. And what's the difference? Well, the difference is the presence of this double bond right here. That extra double bond between those 2 carbons leads to 4 bonds that each carbon has. And since each carbon now has that double bond with one another, that means there's one less bond for each carbon to bond with hydrogen. As a result, there's a loss of these 2 hydrogens, and instead that double bond appears. That's why there's a lack of 2 hydrogens there. So that just explains the concept of unsaturation and saturation a little bit more, what it actually means to not have all possible hydrogens possible. That changes the formula a little bit, and this is really important for the US National Chemistry Olympiad specifically, not so much in an intro or organic chemistry course, because in organic chemistry it's not so much the math or the formulas, but in the Olympiad you do have to worry about this, because a lot of the time you'll be given a formula and asked to draw the structures, and whether it's unsaturated or saturated will help guide you on drawing the correct structure, or all the possible structures, which you haven't learned yet, but a single formula can have multiple structures, and this can help guide you on how to draw them, because some of them can be ringed, some of them can be linear, some of them can have double or triple bonds, so this will be very useful later on. Going back to saturation, I blocked this little bit because we had to cover it first, but alkanes with the formula CnH2n plus 2 are saturated, like we discussed, because all carbons have 4 bonds and all extra bonds are with hydrogen, aka they have all the maximum possible bonds with hydrogen. And now, rings and double/triple bonds disrupt this. And compounds with these are called unsaturated, because it leads to them not having the maximum possible amount of hydrogens they could have. Now let's discuss what degrees of unsaturation is. The degrees of unsaturation are basically just a mathematical way of interpreting a loss of all the possible maximum hydrogens that the hydrocarbon could be bonded to. And it is essentially how many pairs of hydrogens are missing compared to a fully saturated alkane. So like here, for example, between propane and cyclopropane, that formation of a bond between those 2 carbons leads to the loss of 2 hydrogens, and so that's what we call a 1 degree of unsaturation for cyclopropane. Because that means 1 degree of unsaturation is equal to the loss of 2 hydrogens. So here, 1 degree of unsaturation is equal to either the presence of 1 ring or 1 double bond that's disrupting the saturation of the compound. Then if we get into 2 degrees of unsaturation, that means there's 4 missing hydrogens. So this is where you could open up the world to many possibilities that could happen. This will be interesting when you have to draw all the different isomers of which you don't know that yet, but you'll get to it. So 2 degrees of unsaturation could either be 2 rings, 1 ring plus 1 double bond, 2 double bonds, or 1 triple bond, which we have not covered yet, so please don't worry about that yet. But one triple bond would essentially, like, just imagine an extra bond here. And because of that extra bond, we would have to get rid of 2 more hydrogens. So that's what that is, essentially. But yeah. Finally, the formula to calculate degrees of unsaturation. This formula will grow as we learn more about organic chemistry, but for now we're keeping it simple as we're only dealing with hydrocarbons right now. So right now the formula is 2n plus 2 minus H over 2, where n is the number of carbons of the compound and H represents the actual number of hydrogens which the hydrocarbon has. So for example, let's why 2n plus 2 minus H? Well, 2n plus 2 is, remember the formula of the hydrogens in a fully saturated alkane. So in a hydrocarbon that is fully saturated with hydrogens. And then you subtract the actual number of hydrogens to find out how many are missing from how many are missing to be a fully saturated alkane. And since we count 1 degree of unsaturation as 2 missing hydrogens because 1 ring makes 2 hydrogens disappear and 1 double bond makes 2 hydrogens disappear, so that's why we count 1 degrees of unsaturation as 2 missing hydrogens, because we basically want 1 degree of unsaturation to mean, so this is either 1 ring, it's either a ring compound or it has a double bond, so it's easier for chemists to understand. And so you divide by 2 because at the top you'll get the amount of missing hydrogens you have, and you divide by 2 to make it a degree of unsaturation. Let's apply this formula, for example. If we have CH3H6, so your amount of carbons is 3, so it's 2 times 3 plus 2. So this represents the amount of hydrogens that a fully saturated alkane would have, aka an alkane with all the possible hydrogens bonded to, minus the actual amount of hydrogens our compound has, which is 6 over 2. And this will equal the degrees of unsaturation. So if we perform that calculation in the bracket, it'll be 2 times 3, which is 6, plus 2 is 8. So we get 8 minus 6 over 2 equals the degrees of unsaturation. There's no units, by the way. This is just purely for analysis. Then 8 minus 6 is 2. So that means that we have 2 missing hydrogens. And we know 1 ring or 1 double bond causes 2 hydrogens to disappear. So if we want to know how many rings or how many double bonds, we have to divide by 2. And so we get that we have 1 degree of unsaturation for this compound. And that means we either have 1 ring or 1 double bond, which I have not been so formal, but these double bonds are called pi bonds. I will start referring to them as such from now on. So let's draw the structure. If we know it's either 1 ring or 1 double bond, we can draw 2 structures. So we could do carbon, carbon, carbon. I can draw a double bond here, and then just draw in your missing hydrogens. Great, so this would be called propene. You don't have to know that right now, but it would have the formula C3H6. H6. And you see how you're able to easily draw this just based off the degrees of unsaturation, because it tells you if it's a double bond or a ring. Then you could also draw it as a ring. Because of the degrees of unsaturation you found. And this will tie back into something called structural isomerism, which is when a single formula, as we can see, C₃H6, can have different actual structures, which is just, it just has different ways in which the atoms can be arranged, such as here. So, now, to summarize today's lesson, saturation is equal to the maximum hydrogens, and unsaturation equals the missing hydrogens. Cycloalkanes are saturated molecules and single bonds, but form rings, removing 2 hydrogens. Alkenes also reduce hydrogen count due to double bonds. And the degrees of unsaturation count how many hydrogens are missing compared to a saturated formula. Degrees of unsaturation helps predict rings, double bonds, or triple bonds in a molecule. This will be helpful when you get to drawing different isomers. In the next lesson, we'll take these ideas and learn bond line structures, isomerism, and naming, which will allow you to quickly read and draw molecules for U.S. National Chemistry Olympiad. Thank you.